Good morning, guys. So this is IS number 17, testing a claim about a mean. We are going to ask the question, are you getting enough sleep? And this will be about hypothesis tests for mu, for population means. Okay, so our problem is that it's recommended for young adults to get 8 hours of sleep a night. So Mrs. Bakula believes her intro stats to students are getting less than the recommended 8 hours of sleep per night. So to test her belief, take a random sample of 10 students in the class and record the number of hours of sleep for each. Do these data provide convincing evidence that intro to stats students get less than 8 hours of sleep per night using alpha equals 0.05? Okay, so that prompt, do these data provide convincing evidence? Right? Are we convinced? That is always a sign that we're going to do a hypothesis test. Instead of asking us to estimate the mean, they're asking if our data that we have provide convincing evidence for a certain claim. And it appears our claim would be less than 8 hours of sleep per night. Okay, so if we were doing this in class, I would use a random number generator to generate 10 numbers that represent 10 students, and then I would ask those 10 students to tell me the number of hours they got of sleep last night. So I've done this in a previous class, and this was the sample that I got, these numbers here. So 8 hours, then 6 hours. Some people got as low as 3, 3.5, 4.5, and some people as high as 10 and 9. Okay, so we want to calculate the sample mean and standard deviation. One way to do this is to use Statlet, but since we haven't practiced finding mean and standard deviation with our calculators in a while, that's how I'm going to do it. So I turn my calculator on, and hopefully you remember that in order to enter data in order to calculate the descriptive statistics, the mean and standard deviation, we need to enter data into a list and then do that calc one variable statistics. Okay, so I am going to hit stat and then enter over edit. That's how I get to my list. If I already have data in that list, I can scroll up using the arrows to get to the name of the list and hit clear, not delete, clear, and then enter, and that'll clear all the data. So then I enter my numbers. Let's say I have 8, 6, 3.5, 10, 3, 4.5, 5.5, 6, 7, and 9. Okay, remember you have to hit enter after each value. Notice if I scroll back up to highlight the last number, it says L1 to 10. So that's my 10th item. I was supposed to have 10 numbers, so I've done that correctly. Okay, so now I want to calculate that one variable statistic. So I'm going to hit stat, go over to calc, enter over one variable stats, and then tell it the correct list I've been using. I was using L1, so that's fine. Go down and hit enter over calculate. Okay, so there's my mean. That one's obvious. The X bar is 6.25. And then there's lots of other things. We've learned that S and sigma both stand for standard deviation. S is for a sample, sigma is for a population. So if we were saying that set of 10 values was for the whole population, then we would use sigma, but we're not. We're saying that's a random sample of the population, so we use S. So we want the 2.288. Okay, let's write those down. So I have X bar, it said was equal to 6.25 hours of sleep per night. And then S sub X, and I'm using that sub X just to make sure it's clear where I got that from the calculator, was 2.288 hours. Okay, so then number 2 says, state the appropriate hypotheses for a significance test. Notice I'm trying to throw significance and hypothesis interchangeably in there so that you know they mean the same thing. This is a hypothesis test, significance test is the same thing. Okay, so we're going to state those hypotheses and be sure to define the parameter of interest. Okay, so the parameter that we're interested in is the mean, right? We want to know the average for the whole class. We're given the sample mean, so we can use that to test a claim about the population mean. So let's see. We're going to have the null hypothesis and the alternative hypothesis. They're going to be about the same parameter, mu. Let's define mu, where mu is equal to the true mean. let's see, what is it again? The true mean hours of sleep per night. Hours of sleep per night. And we're supposed to be specifically looking at for Intro to Stats students. I'm going to abbreviate Intro to Stats. Okay, so I want to see if I can provide convincing evidence for this claim that students get less than 8 hours of sleep per night. The only one that I can prove is the alternative, right? I can be against the null, which is for the alternative, but I can never prove the null. I can just say I don't have enough evidence to say one way or the other. So we want to prove mu is less than 8, so our null will be that mu is equal to 8, right? That'll be our baseline. Students actually do get 8 hours of sleep per night on average. And then our alternative hypothesis will be that students get less than 8 hours. And then the last thing that I normally put in this section, because this is going to be my state section of the 4-step process, is my significance level. So they told me to use alpha 0.05. I'm going to go ahead and put that in. Okay, so then it says what conditions must be met, check them. Hypothesis tests for means are just like the ones for proportions in that their conditions mirror the conditions used for confidence intervals. So we're going to use those same conditions. If you remember, the first one is the random condition. That's the same for means or proportions. So it told us to take a random sample of 10 students. We have that. Random sample of 10 students. Now I know some of the problems in your book don't always say that it was actually a random sample, but they usually tell you that they're coming from some accredited polling place or some sort of research, and you can trust that those kinds of places are using random samples. Okay, BuzzFeed not so much, but the places mentioned in your book I think you can trust. Okay, the second condition is the same for means and proportions as well. It's the 10% condition. So this is that our sample size of 10 is less than 1/10 of all Intro to Stats students. Okay, so unfortunately, we do not have 100 students in the class, right? So 10 is not actually less than 1/10 of all Intro to Stats students. So this condition is actually not met. And I did this on purpose because I want to talk to you about what we do if on a test or, as you're working one of the homework problems, which probably it shouldn't happen in the homework problems, but just in case you make a mistake, get confused, and you think that one of the conditions is not met, you should still proceed and complete the hypothesis test or confidence interval. And then at the end, we'll just say, because the 10% condition is not met, we cannot be sure that this extends or that this is valid for the population. But we still want to make sure that you do show all of the work and still show that you know how to complete the hypothesis test. Okay, so then the third condition is the normal condition. Okay, so there are 3 different ways to check this, if you remember. The first way is that the population distribution is normal, but unfortunately it doesn't tell us anything about the population of Intro to Stats students, so we don't know that one. The second one is that n can be greater than or equal to 30. Well, unfortunately, n is only 10, so that one's not true either. Then the third one was that the sample distribution could have no strong skew or outliers. We have to check that one. So in order to do that, we have to take our sample data here and sketch a quick graph of the distribution. So I'm just going to sketch a quick dot plot. I'm going to make, let's see, I know I have some half values here, but I'm going to go ahead and put like 3 and 3.5 in the same little dot plot column. There's 4, 5, 6. I need to go all the way up to 10, I believe. Okay, so I have 8 and 6, and then 3.5 and 10. So 3.5 is going to go above 3, 10, and then 3 and 4.5. 4.5 is going to go above 4. 5.5 goes above 5, another 6, a 7, and a 9. Okay, so with so few data points, it's even hard to start seeing a shape, but I definitely think we can say there's nothing crazy about this distribution. There's no strong skew or outliers. So we'll say the sample distribution shows no strong skew or outliers. Okay, that condition is met. All right, so let's move forward. Number 4, well, first of all, if you think about how we do these hypothesis tests for proportions, our next step would be to think about to complete our do section. So we'd be thinking about the general formula, then the specific formula for the test statistic, showing our work, showing the picture, and then the answer. So we need to think about what our picture is going to look like and what the test statistic are. We're not dealing with sample proportions anymore, so we don't have p hat and p anywhere in there. We're going to have a distribution that has the mean and standard deviation of the sampling distribution of x bar. And we learned about these back when we talked about the central limit theorem. So this is that mu sub x bar. Okay, if you remember, the mean for sample means is just the population mean, which for us we're assuming is 8. Notice it also says calculate the values. Now the standard deviation for x bar, right, was equal to sigma divided by the square root of n, sigma being the population mean divided by the square root of n. Now, unfortunately, we don't know the population mean, similar to the situation for confidence intervals, so we're going to estimate it with the sample standard deviation. So this is going to be approximately equal to that thing we called the standard error for x bar, which is the sample standard deviation divided by the square root of n. Now we can calculate that. We know the sample standard deviation, we wrote it down above, is 2.288 divided by the square root of n, which is 10. Again, I calculated the sample standard deviation up here. Okay, so now I can calculate that. I'm gonna get quit out of that, 2.288 divided by second square root of 10. Okay, and I get 0.72, let's see, it's 7235. I think 3 decimal places is enough, so I'm going to round to 0.724. 0.724. Okay, so it says draw a picture and then calculate the test statistic. So my picture looks kind of like a normal curve. Well, it will look pretty much like a normal curve. I don't expect you to try to make it look different necessarily. Ugh, my normal curve was not great. That's all right. We'll label it just the same. We'll put the mean in the middle. So this is 8. And then we'll go up 1, 2, 3 standard deviations and down 1, 2, 3 standard deviations. So let's see. Going up is easy. 8 plus my standard error of 0.724 is going to be 8.724. But then to calculate the rest, I'm just going to use my calculator. So 8.724 plus another standard error, 0.724. And then I'm going to go ahead and type in the next one too. Okay, so 9.448. Turn my paper here a little bit. 9.448. And then the next standard error up is 10.172. And then I need to go down. So I'm going to go 8 minus 0.724 and do that 3 times. Oops. 0.724. Oh, I did that last one wrong, didn't I? Darn. Okay, minus 0.724. That's my second time, and then there's my third. Got it. Okay, so 7.276 is first. 7.276, and then 6.552, and then 5.828. Okay, so after I've drawn my picture, I think I may have made a mistake in the confidence intervals notes. This is not actually a normal curve, remember, because we are not using the population standard deviation. We're using the sample standard deviation, which introduces even more variability and changes depending on the sample that we take. So this is actually the t distribution. Looks like a normal curve, but has a little bit more area in the tails. So I label this as t, and then I label it with the degrees of freedom. So remember, degrees of freedom are n minus 1, so 10 minus 1 would be 9. Okay, sorry about that, guys, but that's what we should be labeling. And then we also want to go ahead and put on here our sample mean. So our sample mean was 6.25. 6.25 is going to be, let's see, a little bit closer to 6.552, right? So this is the area that I'm actually interested in. this value or more extreme, so farther away from the mean, in this case it'd be less than the mean. So I'm looking for that little area there. I can already tell my p-value is not going to be very big. So again, that's the probability that my sample mean x bar is less than or equal to my sample mean 6.25 from these sample results. Okay, all right, so now I need to calculate my test statistic. So my test stat, the general formula is the same as it was for proportions. Statistic minus parameter divided by the standard deviation. Okay, except for this time, we don't have z, right? We don't have a z-squared because that's for normal distributions. We have to use that student t distribution. So this is a t value. The statistic is the sample mean, x bar. The parameter is the population mean, mu. We're estimating the standard deviation with that s divided by the square root of n, right? We don't know sigma, so we have to use s. Okay, that's my specific formula. So now let's plug in the numbers. T is going to be equal to 6.25 for my sample mean minus 8 for my population mean divided by my sample standard deviation was 2.288 divided by the square root of the sample size, which is 10. Okay, so if I put parentheses around the top and parentheses around the bottom, that'll make this a lot easier when I type it in my calculator. So I'm indicating that on my paper so you can see where it's going into my calculator. Okay, so parentheses 6.25 minus 8, end my parentheses, then divide by a new set of parentheses, my sample standard deviation 2.288 divided by the second square root of 10. Now notice that little blinking arrow is still underneath the line that has the standard deviation. I don't want to put my end of parentheses there, so I'm going to use my right arrow to get out of that. See how it's not underneath the line anymore? And then I put my last set of parentheses. Hit enter. Okay, so I get negative 2 point, let's do 3 decimal places, so 419. Negative 2.419 is my t value, my test statistic. Now, I know for sure that that's not a probability because probabilities are never negative and never outside of between 0 and 1. So this definitely is not my p-value. P-values are probabilities, but I can use this to find my p-value. Okay, so there are 2 options. One is to use table A3, and I'm going to show it to you just because it's traditional, but I don't like this way necessarily because it's no longer going to give us a specific value, right? Table A2 with the normal distribution gives us a specific value. This one will not. We haven't done this before. We've used table A3, but not in this way. What we have to do is go to row that refers to your degrees of freedom. So our degrees of freedom are equal to, again, that 10 minus 1 or 9. And then we have to find the closest t value and match to the area in one tail. Okay, before we were using the area in 2 tails, this time we're going to match the area in 1 tail because we just have 1 tail here. Okay, so let's see this. We're going to the degrees of freedom row 9, and they're going to find the closest t value to our negative 2.419. Okay, so I go to degrees of freedom 9, and then I scan over, and first of all, I realize these are all positive. So I think about how if I were to flip this picture and have that tail be on the right side, the t value would be positive and it would be the same area just on the right. So I'm going to think about this being a positive. That's what you have to do. Okay, so I'm looking for 2.419. All right, it looks like for the degrees of freedom row 9, 2.419 would be between these 2 values. Okay, so I go up to my area in 1 tail. That means my p-value will be between 0.01 and 0.025. Okay, so that tells us that my p-value is between 0.01 and 0.025. Now, not super specific. Oh, sorry. Didn't realize I was too high for that. P-value is between 0.01 and 0.025. It's not super specific, but it does tell me that I'm going to reject the null because regardless of whether it's 0.01 or 0.025, both of those are less than our significance level of 0.05. Okay, so that's one option. The other option, which I like much better, is to use technology for this. So you're going to use the calculator function. This is again, or TCDF. And it asks for a lower, an upper, and then a degrees of freedom. So let's write those. Oh, by the way, to get to TCDF in your calculator, it's another one of those distributions. So we go to second and then distribution, that vars key. It's the sixth one down, TCDF. So we hit enter over that. And then let's see, our lower bound in our picture here is like super, super, super negative. So like negative 10,000 would work. And then our upper bound is that t value we found. So negative, make sure you press the negative key down here. The negative, not the minus, but the negative. 2.419. And then my degrees of freedom for this one are just 9. Okay, so I enter all that, paste. And there is my p-value. So let me enter or write down what I entered there. A lower value of negative 10,000, that's anytime you have a left tail. The upper bound for my t-value was negative 2.419, and my degrees of freedom were 9. That gave me a value of 0.019. 3 decimal places is plenty. Okay, so again, I really strongly suggest that you use this TCDF function, and these are the things you actually have to enter in order to get that. And then it'll give you a much more exact p-value. Notice that 0.019 would be between 0.01 and 0.25. So table A3 is not wrong, it's just not very specific. Okay, so let's go ahead and make our conclusion. I do want to write out one more time what the options for the conclusion are, just because I think some students are still kind of confused for that. So I'm just putting this, off to the side. This is not the conclusion. These are just my options. If my p-value is less than alpha, which in this case is 0.05, right? That's not always 0.05, but that's what it is here. Then the colon means then we reject the null. Remember, H naught stands for the null. On the other hand, if my p-value is greater than alpha, which again is 0.05, then I fail to reject the null. Interpreting that p-value, I would say, assuming that the true mean really is 8 hours of sleep, if the p-value is less than 0.05, then that we have a probability that's so low of getting a sample result like this or more extreme that we think that the assumption is not actually true. We reject the assumption, the null. On the other hand, if that p-value is greater than 0.05, then it's possible that the null is true, and we don't have enough evidence to reject the null, right? We can't say the null is true for sure. We just don't have enough evidence against it. Okay, so let's write out our conclusion. Again, this is just to help you remember how to make your decision. Okay, so since our p-value, which is equal to 0.019, is less than our alpha of 0.05, we reject the null. Then you always have to put that in context, right? If you tell somebody out on the street that you're rejecting the null, they'll have no idea what you're talking about. So we say we have convincing evidence. And then we talk about the parameter. So that we phrased up above, it was from the original question, that the true mean hours of sleep per night for intro to stats students. So that the true mean hours of sleep per night for intro to stats students. And again, we're rejecting the null, so we think the alternative is true. So that mean is less than 8. is less than 8 hours. Another way to say that would have been to rephrase the question. We have convincing evidence that intro to stats students get less than 8 hours of sleep per night. Right? That would be another way to say it, but we've said this something similar here. Okay, so that is our first significance test for means. In the next part, we're going to write down our big ideas and then follow that 4-step process, which this is broken up. And actually, I'm going to go ahead and put on here how that 4-step process is on here. Let's see. This would be mostly our state. We're missing something. Oh, no, I think all of state is there. 3 would be our plan, but we're missing the name of the test. So I'll give that to you on the next page. Let's see. All of this is the do, right? It's broken out quite widely. We'll summarize it better on the next page. And then this last part, number 7, was our conclude. Okay. All right. See the next video for the big ideas.